Mars will kill you in ways Earth never could, but thousands of people are signing up to go anyway. What could possibly make living on a frozen, radiation-soaked desert worth abandoning everything you've ever known? And here is a question. If you could bring only 3 things from Earth to Mars to remind you of home, what would they be? Let us know in the comments. I'll pin the most creative answer. Now let's begin. Mars has captured our imagination for centuries, but only recently have we begun to understand what it would actually take to survive there. Thanks to missions like Perseverance, Curiosity, the Mars Reconnaissance Orbiter, and dozens of other spacecraft, we've gathered data that paints a vivid picture. Spoiler alert, it's both more challenging and more fascinating than you might think. This isn't just about planting a flag and coming home. We're talking about living, breathing, eating, sleeping, and building a life on a planet that wants to kill you at every turn. Yet despite all the dangers, Mars might be the only other world in our solar system where humanity could truly establish a second home. Let me take you through what a day, a week, a year on Mars would actually look like. We'll explore the science behind survival, the technology that could make it possible, and the profound ways living on another planet would change you, not just physically, but mentally and spiritually. Because when you're standing on Mars, looking back at Earth as a pale blue dot in the night sky, you'll feel something that no human in history has ever felt. You'll be a citizen of 2 worlds. First things first, let's talk about the most basic thing you need to stay alive: air. On Earth, you take breathing for granted. You walk outside, you inhale, and your lungs fill with a mixture of 78% nitrogen, 21% oxygen, and trace amounts of other gases. Simple, automatic, life-sustaining, but on Mars? The atmosphere is nothing like ours. It's composed of 95% carbon dioxide, with only trace amounts of nitrogen and argon, and barely any oxygen at all. If you tried to breathe Martian air without a spacesuit, you wouldn't just suffocate, you'd experience something far worse. The atmospheric pressure on Mars is less than 1% of Earth's pressure at sea level. That's about the same pressure you'd find at an altitude of 35 kilometers above Earth. At that pressure, something terrifying happens to the human body. Your blood starts to boil. Not because it's hot, but because the pressure is so low that water vaporizes at body temperature. This process is called ebullition, and it would cause the moisture in your tissues to turn into gas. Your skin would swell, your blood vessels would expand, and within about 15 seconds, you'd lose consciousness. Death would follow shortly after. So, rule number 1 on Mars: you're never, ever taking off your spacesuit outside the habitat. But let's say you're inside a pressurized habitat, a sealed structure where the air is Earth-like and breathable. How do you keep that air fresh? You can't just crack open a window when things get stuffy. Every molecule of oxygen you breathe has to be manufactured, recycled, or imported from Earth. Current life support systems, like those used on the International Space Station, can recycle about 90 to 95% of water and oxygen. They break down carbon dioxide that you exhale, extract the oxygen, and release the carbon. They filter humidity from the air, purify it, and return it to the water supply. It's a closed-loop system, but it's not perfect. You'll still need resupply missions from Earth, at least in the early years, to top off what's lost. There's also a technology called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment that NASA tested on the Perseverance rover. MOXIE successfully produced oxygen by pulling carbon dioxide out of the Martian atmosphere and splitting it into oxygen and carbon monoxide. It's like a tree, but mechanical. If we can scale this technology up, future Mars colonists could generate their own breathable air directly from the planet's atmosphere. Imagine that, breathing Martian air that you manufactured yourself. It's not science fiction anymore, it's engineering in progress. If you're enjoying this deep dive into the realities of Mars, hit that subscribe button and give this video a thumbs up. It really helps the channel grow, and I've got so much more cosmic content coming your way. Now let's talk about water. You need it to drink, to grow food, to manufacture fuel, and to maintain your habitat. Fortunately, Mars has water, lots of it. The polar ice caps contain frozen water mixed with carbon dioxide ice, and beneath the surface, especially at higher latitudes, there are vast deposits of subsurface ice. The Mars Reconnaissance Orbiter has mapped these ice deposits using ground-penetrating radar, and we know that in some regions you could dig down just a meter or two and hit solid ice. But here's the catch, that ice isn't pure. It's mixed with Martian soil or regolith, which contains a nasty chemical called perchlorate. Perchlorates are salts that are toxic to humans. They interfere with your thyroid function and can cause serious health problems if ingested. So you can't just melt Martian ice and drink it. You'd need to process it, filter out the perchlorates, and purify the water before it's safe. That adds complexity, energy requirements, and potential points of failure to your life support system. Still, having accessible water on Mars is a game changer. It means you don't have to bring all your water from Earth, which would be impossibly expensive. Instead, you can practice what's called in situ resource utilization, ISRU for short. You use what's already there. You mine the ice, purify it, drink it, use it to grow crops in your greenhouse, and even split it into hydrogen and oxygen to create rocket fuel. Water is the most valuable resource on Mars, and learning to harvest and manage it will determine whether a colony can become self-sufficient or remain dependent on Earth. Next, let's talk about temperature. Mars is cold, really, really cold. The average temperature on Mars is around minus 63 degrees Celsius, which is minus 81 degrees Fahrenheit, but that's just the average. At the equator during the summer, daytime temperatures can climb to a relatively balmy 20 degrees Celsius, about 68 degrees Fahrenheit. Not bad, right? You could almost wear a t-shirt. But when the sun sets, temperatures plummet to minus 73 degrees Celsius, or minus 99 degrees Fahrenheit. That's a temperature swing of nearly 100 degrees in a single day. At the poles, it gets even worse. Winter temperatures can drop to minus 125 degrees Celsius, which is minus 193 degrees Fahrenheit. At those temperatures, carbon dioxide freezes out of the atmosphere and falls as dry ice snow. The Martian environment is brutal, and your habitat has to protect you from these extremes. You'll need thick insulation, probably made from Martian regolith, to keep heat inside. You'll need reliable heating systems, likely powered by nuclear reactors or concentrated solar arrays. And you'll need backup systems because if your heater fails during a Martian night, you could freeze to death in hours. But temperature isn't the only environmental hazard. There's also radiation. Earth's magnetic field and thick atmosphere shield us from most of the harmful radiation that comes from space, cosmic rays from distant supernova, and solar particles ejected by our sun. Mars has neither a global magnetic field nor a thick atmosphere. Its magnetic field collapsed billions of years ago, and its atmosphere is too thin to provide meaningful protection. As a result, the surface of Mars is constantly bombarded by radiation. On Earth, the average person receives about 3 millisieverts of radiation per year from natural sources. On Mars, you'd receive about 700 millisieverts per year. That's more than 200 times higher. Over time, this radiation increases your risk of cancer, damages your DNA, and can even cause acute radiation sickness during solar storms. A single, large solar event could deliver a lethal dose of radiation if you're caught outside without proper shielding. So how do you protect yourself? The answer is mass. Thick walls. Martian regolith is actually an excellent radiation shield. If you pile 2 meters of regolith on top of your habitat, you can reduce radiation exposure down to about 50 millisieverts per year, closer to what astronauts experience on the International Space Station. Some designers have proposed building habitats inside lava tubes, natural tunnels formed by ancient volcanic activity. These tubes could provide natural shielding and stable temperatures. Others suggest printing habitats using 3D printers that mix regolith with binding agents to create thick, protective walls. You might also spend a lot of time underground, not in a grim dystopian sense, but as a practical necessity. Underground habitats would be shielded from radiation, insulated from temperature swings, and protected from dust storms. They'd be your safe haven, your home base, your fortress against the Martian environment. That brings us to dust. Martian dust is everywhere. It's fine, it's sticky, and it's sharp. Under a microscope, Martian dust particles look like tiny shards of glass. They cling to everything: spacesuits, equipment, solar panels. They get into seals, into joints, into filters. During dust storms, which can last for weeks and occasionally engulf the entire planet, visibility drops to 0 and sunlight is blocked. Solar panels stop generating power. Temperatures drop even further. You're essentially trapped inside, waiting for the storm to pass. The dust is also a health hazard. If it gets into your lungs, it could cause inflammation and respiratory problems similar to silicosis, a disease that affects miners on Earth. So, every time you come back inside from an EVA, an extravehicular activity, you'd have to go through a rigorous decontamination process. You'd use brushes, vacuum systems, and airlocks to remove as much dust as possible before entering the main living area. It's tedious, it's time-consuming, but it's essential. Let's pause for a moment and zoom out. Why does all of this matter? Why go through all this trouble? Because Mars represents something profound. It's the next chapter in the human story. For the first time in our species' history, we have the technology to become a multi-planetary civilization, and Mars is the best candidate. It has a day length similar to Earth's, 24 hours and 37 minutes. It has seasons, polar ice caps, and evidence of ancient rivers and lakes. Billions of years ago, Mars had a thicker atmosphere and liquid water on its surface. Life may have even emerged there, just as it did on Earth. In fact, one of the most exciting discoveries in recent years came from NASA's Perseverance rover. In July of 2024, Perseverance drilled into a rock called Cheyava Falls in an ancient river channel named Neretva Vallis. The sample, nicknamed Sapphire Canyon, contains what scientists call potential biosignatures, chemical and structural features that could have been produced by ancient microbial life. The rock contains organic carbon, phosphate, iron, and sulfur arranged in distinct patterns that on Earth are often associated with biological activity. Two minerals stood out, vivianite and greigite. On Earth, these minerals commonly form through microbial processes in oxygen-poor, water-rich environments. The Martian rock even shows a bullseye pattern, vivianite-rich rims surrounding greigite-enriched cores that looks eerily similar to patterns created by microbes in Earth's sediments. Scientists are careful to say this is not definitive proof of life. There could be unknown chemical processes that produce the same signatures, but it's the closest we've ever come. And the only way to know for sure is to bring that sample back to Earth and study it in laboratories far more sophisticated than anything we can send to Mars. This is why Mars Sample Return is such a critical mission. Those sealed tubes that Perseverance has been collecting could contain evidence that we are not alone in the universe, that life has arisen independently on at least 2 worlds. Imagine what that would mean. It would suggest that life is not a cosmic fluke, but a natural outcome of chemistry and time. It would imply that the universe is teeming with life, waiting to be discovered, and it would fundamentally change how we see ourselves and our place in the cosmos. But back to the practicalities of living there. Let's talk about food. You can't order pizza on Mars. There's no supply chain, no grocery store, no drive-through. Every calorie you consume has to be grown, manufactured, or shipped from Earth. In the early days of a Mars colony, most food would come from Earth. Pre-packaged meals, freeze-dried rations, carefully balanced to provide nutrition and prevent food fatigue. But shipping food from Earth is expensive, about $10,000 per kilogram, potentially more, depending on the mission architecture. Over time, a sustainable colony needs to grow its own food. That means greenhouses. Hydroponic or aeroponic systems where plants grow without soil, their roots bathed in nutrient-rich water or mist. You'd grow staples like potatoes, lettuce, tomatoes, beans, and grains. Research on the International Space Station has already shown that many crops can grow in microgravity, and Mars has 38% of Earth's gravity, not ideal, but workable. The real challenge is providing enough light, water, and nutrients in a closed system. Martian regolith can't be used directly as soil because of those perchlorates we mentioned earlier, but with treatment, washing, filtering, adding organic matter, it could be converted into something plants can grow in. You'd also need pollinators. On Earth, bees do the job. On Mars, you might use small robotic drones or simply hand-pollinate each plant. It's labor-intensive, but necessary. There's another option being explored: lab-grown meat. Cultured protein created from animal cells grown in bioreactors. No animals, no slaughter, just meat produced in a controlled environment. This could provide colonists with protein without the resource demands of raising livestock. Imagine eating a steak on Mars that was never part of a cow, just cells that grew in a vat, indistinguishable in taste and texture from the real thing. It sounds like science fiction, but companies on Earth are already making progress toward commercial production. Then there's the psychological side of eating. Food is culture, it's comfort, it's memory. When you're millions of kilometers from home, a familiar meal can be a powerful antidote to loneliness. So, Mars colonists would likely have small luxuries: spices, chocolate, coffee, things that make life worth living. These wouldn't just be frivolous, they'd be essential for mental health. Speaking of mental health, let's talk about isolation. Mars is far, really far. At its closest approach to Earth, Mars is about 55 million kilometers away. At its farthest, it's over 400 million kilometers. Light takes between 3 and 22 minutes to travel from Earth to Mars, depending on where the planets are in their orbits. That means a conversation with someone on Earth would have a delay of 6 to 44 minutes round trip. You can't have a real-time chat. You can't call home when you're feeling down and hear a loved one's voice immediately. Every communication is a message sent into the void, waiting for a reply that might not come for nearly an hour. This isolation is profound. You'd be more alone than any human has ever been. Even astronauts on the International Space Station can see Earth out the window, a vibrant blue marble just 400 kilometers below. But on Mars, Earth would be just another star in the sky, a bright one, sure, but tiny and distant. You'd feel the weight of that distance every single day. The psychological effects of isolation and confinement are well documented. Studies of Antarctic research stations, submarine crews, and long-duration space missions show that people experience mood swings, depression, irritability, and cognitive decline. The phenomenon is sometimes called the third quarter effect, a dip in morale about 3/4 of the way through a long mission. On a Mars mission, which could last 2.5 years for a round trip, that's a serious concern. NASA and other space agencies are studying countermeasures. Virtual reality could let you walk through a forest on Earth, hear birds singing, feel simulated sunlight on your face. Structured schedules, regular exercise, creative outlets, and strong social bonds within the crew are all essential. You'd also need private space, a small cabin where you can close the door, be alone with your thoughts, and decompress. Living in close quarters with the same people for years tests even the strongest relationships. By the way, if you're fascinated by the challenges of long-term Mars habitation, I have another video called Why the First Humans on Mars Will Never Return to Earth that explores the physical and physiological changes that might make coming back to Earth impossible. Check it out after this one. The link is in the description and on the card above. Now let's talk about gravity. Mars has about 38% of Earth's gravity. That might sound like fun. You could jump higher, lift heavier objects, but it comes with serious health consequences. Astronauts on the International Space Station, which is essentially in zero gravity, experience rapid bone density loss, muscle atrophy, and cardiovascular deconditioning. They lose about 1 to 2% of their bone mass per month. On Mars, gravity is present, but it's weak. Early studies suggest that partial gravity might slow bone and muscle loss compared to zero gravity, but it won't stop it entirely. Over months and years, your bones would become more fragile. Your muscles would weaken. Your cardiovascular system would adapt to the lower gravity, and your heart might lose the strength needed to pump blood efficiently against Earth's gravity. If you ever return to Earth after spending several years on Mars, you might not be able to stand up. You might be wheelchair-bound, your body too weak to support its own weight. This is one reason why some scientists believe the first Mars colonists might never come home. They'd be permanently adapted to Mars, their bodies transformed by the environment. Exercise would be critical. You'd spend hours every day on resistance machines, treadmills, and other equipment designed to stress your bones and muscles. It would be tedious, exhausting, but absolutely necessary. Without it, your body would waste away. There's also the question of reproduction. If humans are going to establish a permanent presence on Mars, eventually people will have children there. But we have no idea what pregnancy and fetal development would look like in partial gravity. Would a fetus develop normally? Would the skeletal system form correctly? Would there be complications during birth? These are questions we can't answer yet. Some researchers have proposed spinning habitats, rotating structures that create artificial gravity through centrifugal force. But building something like that on Mars would be a massive engineering challenge. Let's talk about energy. Everything on Mars requires power. Your habitat's life support, heating, water purification, food production, communications, manufacturing, all of it needs a constant, reliable energy supply. Solar panels are an obvious choice. Mars gets plenty of sunlight, though it's about 43% less intense than on Earth because Mars is farther from the Sun. Solar panels work, but they have limitations. Dust storms can block sunlight for weeks. Dust accumulation on the panels reduces efficiency. You'd need cleaning systems, backup batteries, and redundant power sources. Nuclear power is the other option. Small modular reactors could provide steady, reliable energy regardless of weather conditions or time of day. NASA has been developing a technology called kilopower, a small fission reactor that could generate 10 kilowatts of continuous power for over 10 years. A few of these reactors could power an entire Mars base. Nuclear energy doesn't rely on sunlight, doesn't produce greenhouse gases, and provides a stable baseline that solar can supplement. You might also tap into geothermal energy. Mars is volcanically inactive now, but there may still be residual heat beneath the surface in certain regions. Drilling deep enough could access that heat and convert it into electricity. It's speculative, but worth exploring. Transportation on Mars is another fascinating challenge. The planet is huge, about half the diameter of Earth, but with no oceans. so the land area is roughly equal to Earth's total land mass. If you want to explore, conduct research, or establish multiple outposts, you need vehicles. Rovers, of course, but also potentially aircraft. Mars's thin atmosphere makes flight difficult, but not impossible. NASA's Ingenuity helicopter proved that powered flight can work on Mars. Future aircraft could be larger, more capable, and able to carry cargo or even passengers across vast distances much faster than ground vehicles. There's also the possibility of underground transit. Lava tubes could serve as natural highways, shielded from radiation and temperature extremes. You could build tunnels connecting different habitats, creating a network of safe passages beneath the surface. Let's talk about construction. Building on Mars isn't like building on Earth. You can't just pour concrete and stack bricks. Every material has to be sourced locally or brought from Earth at enormous cost. The most promising technique is 3D printing using Martian regolith. You mix the regolith with a binding agent, maybe water, maybe sulfur, maybe a polymer, and print it layer by layer to create structures. Researchers have already demonstrated this on Earth using simulated Martian soil. Another approach is inflatable habitats. You bring a lightweight, compact module from Earth, inflate it on Mars, and then cover it with regolith for radiation shielding and insulation. Companies like Bigelow Aerospace and others have developed inflatable modules that are surprisingly strong and durable. You could also build inside natural structures. Lava tubes, as I mentioned earlier, are tunnels formed by flowing lava billions of years ago. Some of these tubes are enormous, large enough to fit entire cities inside. They offer natural protection from radiation, micrometeorites, and temperature swings. Sealing off sections of a lava tube and pressurizing them could create vast habitable spaces with minimal construction. It's like living in a cave, but a cave that could house thousands of people. The architecture of Mars habitats would be unlike anything on Earth. Form follows function in the most extreme sense. Every design choice is driven by survival. Airlocks would be everywhere, multiple redundant systems to prevent catastrophic pressure loss. Windows would be small and thick, perhaps made of transparent aluminum or advanced plastics that can withstand pressure differentials and radiation. The interior spaces would be modular, reconfigurable, designed to maximize efficiency and psychological well-being. Colors and lighting would matter enormously. Studies show that lighting affects mood, circadian rhythms, and productivity. On Earth, we take natural daylight for granted. On Mars, especially if you're living underground or in a windowless module, you'd rely on artificial lighting tuned to mimic Earth's day-night cycle. You might have rooms painted in calming blues and greens, artwork on the walls, plants growing in every available space. These aren't luxuries, they're necessities for mental health. Now let's talk about communication beyond just staying in touch with Earth. Within a Mars colony, you'd need robust local networks. High-speed internet, video calls between modules, access to entertainment and educational content, virtual reality experiences. You'd want to stay connected to human culture, to watch movies, read books, listen to music, learn new skills. A digital library containing humanity's accumulated knowledge would be essential. In a sense, Mars colonists would be the custodians of human civilization, carrying our culture and history to a new world. There would also be scientific communication. Mars would become the greatest natural laboratory in human history. Geologists would study its rocks to understand planetary formation. Astrobiologists would search for signs of past or present life. Atmospheric scientists would track weather patterns and dust storms. Astronomers would take advantage of Mars's position in the solar system to observe phenomena that are difficult or impossible to see from Earth. All of this research would be transmitted back to Earth, advancing our understanding of the universe. But here's something profound. Over time, Mars colonists would develop their own culture, their own slang, traditions, and ways of seeing the world. They'd celebrate Martian holidays, maybe the anniversary of the first landing or the first child born on Mars. They'd adapt Earth sports and games to low gravity. They'd create art inspired by Martian landscapes, the towering volcanoes, the vast canyons, the swirling dust storms. A uniquely Martian identity would emerge, distinct from any culture on Earth. This raises a question that might seem trivial but is actually quite important. What time would you use on Mars? A Martian day, called a sol, is 24 hours and 39 minutes long, close to Earth's day but not identical. Do you stick to Earth time and slowly drift out of sync with the Martian day-night cycle? Or do you adopt Martian time and accept that you're no longer on the same clock as Earth? Early missions have used mission time, synchronized to specific locations on Mars, but for a permanent colony you'd probably adopt local Martian time divided into months and years based on Mars's orbit around the Sun, which takes 687 Earth days. Seasons on Mars are longer than on Earth. Spring in the Northern Hemisphere lasts about 7 months. Summer lasts 6 months. Autumn lasts 5 months. Winter lasts 4 months. The seasons are also more extreme because Mars has a more elliptical orbit than Earth. When the Southern Hemisphere is tilted toward the Sun and Mars is closest to the Sun in its orbit, southern summers are hotter and shorter. Northern winters during this time are longer and colder. These variations would shape agricultural cycles, mission planning, and daily life. Let's talk about one of the most ambitious ideas in space exploration: terraforming Mars. This is the concept of transforming Mars into a more Earth-like planet, with a thicker atmosphere, warmer temperatures, and eventually liquid water on the surface. It's the ultimate long-term vision, making Mars a place where you could walk outside without a spacesuit and breathe the air. The idea is tantalizing, but the challenges are immense. Mars lost its atmosphere billions of years ago because it lost its magnetic field. Without a magnetic field, solar wind, a stream of charged particles from the Sun, stripped away the atmosphere over millions of years. To terraform Mars, you'd need to thicken the atmosphere, warm the planet, and ideally restore some kind of magnetic protection. One proposal involves releasing the carbon dioxide trapped in Mars's polar ice caps and in the regolith. If you could warm the planet enough, this carbon dioxide would sublimate into the atmosphere, creating a greenhouse effect that would warm Mars further, releasing more carbon dioxide in a positive feedback loop. You could warm the planet using giant mirrors in orbit to focus sunlight onto the ice caps, or by detonating nuclear devices to release subsurface volatiles. Yes, people have seriously proposed nuking Mars. It sounds crazy, but the physics checks out, at least in theory. Another idea is to manufacture greenhouse gases far more potent than carbon dioxide. Gases like sulfur, hexafluoride, or perfluorocarbons, and release them into the Martian atmosphere. These gases trap heat much more effectively than carbon dioxide and could warm the planet with relatively small amounts. But here's the problem: even if you could thicken the atmosphere and warm Mars without a magnetic field, solar wind would just strip it away again over millions of years. Some scientists have proposed creating an artificial magnetic field by placing a giant magnetic dipole at the Mars-Sun Lagrange point, a gravitational balance point between Mars and the Sun. This magnetic shield would deflect solar wind and protect the atmosphere. It's an idea that sounds like science fiction, but it's been studied seriously by NASA researchers. Even with all of this, terraforming Mars would take centuries, maybe millennia. It's not something the first colonists would see completed. It would be a project for generations, a commitment to a future where your great-great-great-grandchildren might walk on a Mars transformed into a new Earth. But let's be honest, we don't know if terraforming is even ethical. If Mars ever had life, if microbial organisms still exist beneath the surface in subsurface aquifers or ice deposits, do we have the right to alter the planet so drastically? Shouldn't we study Mars as it is, preserve it as a natural laboratory, before we change it forever? These are questions without easy answers, debates that will shape humanity's relationship with Mars for generations. Let's shift gears and talk about something deeply personal, what it would feel like to live on Mars. Imagine you've been there for 6 months. The initial excitement has worn off. The routines have set in. You wake up in your small sleeping pod, the low hum of life support systems, a constant background noise. You check the radiation monitor, levels are normal. You check the weather report, another dust storm forming to the east, but it should miss your base. You go through your morning routine. Exercise, breakfast, systems check. You put on your spacesuit, a process that takes 15 minutes even when you're practiced at it, and step into the airlock. The outer door opens and you step onto the Martian surface. The gravity feels light, every step a little bounce. The sky is a pale salmon color, the sun a shrunken disk. The landscape stretches out, desolate and beautiful in its starkness. You have work to do today. Maybe you're collecting rock samples, repairing a solar panel, or setting up a new experiment. The work is slow, methodical. Your gloves are thick, making fine motor tasks difficult. Your breathing sounds loud inside the helmet. After a few hours, you return to the airlock, go through decontamination, and re-enter the habitat. Lunch is a meal you grew yourself. Tomatoes and lettuce from the greenhouse, protein from cultured cells. It tastes good, a small victory. In the afternoon, you have a video call scheduled with family on Earth. The delay is frustrating. You say something, wait 12 minutes, hear their response, wait 12 minutes to respond. But seeing their faces, hearing their voices, even delayed, is a lifeline. Evening is yours. Maybe you read, watch a movie, play a game with your crewmates. Maybe you spend time in the greenhouse, tending plants, enjoying the greenery and the feeling of life. Maybe you just sit by one of the small windows and watch the sun set, the sky fading from salmon to deep purple to black, stars emerging in impossible clarity. At night, you might go outside again. The stars on Mars are breathtaking. With no light pollution, minimal atmosphere, and no clouds, the Milky Way sprawls across the sky in a river of light. You can see more stars than you ever could on Earth. You find Earth in the sky, a bright blue star near the sun. Your home world, impossibly distant. You feel small, fragile, yet part of something vast and magnificent. This is life on Mars. It's hard, it's dangerous, it's lonely, but it's also awe-inspiring, meaningful, and profoundly human. You're a pioneer, an explorer, part of the story of our species taking its first steps toward becoming a spacefaring civilization. There's also the question of governance. Who makes the rules on Mars? In the early days, it would probably be mission control back on Earth, with the crew commander having authority on the ground. But as the colony grows, as more people arrive and settle permanently, they'll want self-governance. They'll want a say in the decisions that affect their lives. Would Mars be a democracy, a technocracy, a collection of independent settlements, each with its own governance structure? The Outer Space Treaty of 1967 states that no nation can claim sovereignty over celestial bodies, but it doesn't address permanent settlements or private colonies. There are legal grey areas that will need to be resolved. There's also the question of economics. What would the economy of Mars look like? In the beginning, it would be entirely dependent on Earth. Every resource, every piece of equipment, every person would come from Earth at enormous expense. But over time, Mars could develop its own economy based on what it has that Earth doesn't. One possibility is scientific research. Mars is a unique environment for studying planetary science, astrobiology, and the history of the solar system. Data, discoveries, and samples from Mars would have immense value to the scientific community on Earth. Another possibility is resource extraction. Mars has minerals and metals that could be mined and processed, while shipping raw materials back to Earth wouldn't make economic sense given the cost of transport. Mars could supply resources to other space-based operations, asteroid mining missions, lunar bases, spacecraft traveling through the solar system. There's also the possibility of intellectual property. Mars colonists would be solving unprecedented engineering challenges. The technologies they develop, life support systems, radiation shielding, food production in hostile environments, could have applications on Earth, especially in extreme environments like deserts, polar regions, or even underwater habitats. Patents and innovations from Mars could generate revenue. Tourism is another long-term possibility. Imagine wealthy individuals paying millions of dollars for the chance to visit Mars, to walk on another planet, to experience the ultimate adventure. It sounds far-fetched, but space tourism is already beginning on a smaller scale with suborbital flights and trips to the International Space Station. As technology improves and costs decrease, Mars tourism could become a reality. But let's be clear, the first colonists won't be tourists. There'll be scientists, engineers, technicians, highly trained professionals selected for their skills, physical health, and psychological resilience. They'll undergo years of training, learning everything from emergency medicine to equipment repair to piloting spacecraft. They'll be among the most capable humans who have ever lived, because they'll have to be. The selection process for Mars colonists would be rigorous. Physical fitness is essential, but psychological traits might be even more important. You need people who can handle stress, work well in teams, adapt to changing circumstances, and maintain morale during long periods of isolation. Creativity, humor, and emotional intelligence would be valuable traits. You'd also want diversity, not just in skills, but in perspectives, cultures, and backgrounds. A colony benefits from varied viewpoints and problem-solving approaches. There's also the question of permanence. Would colonists go knowing they might never return? Or would missions be rotational, with people spending a few years on Mars before returning to Earth? The answer probably depends on the stage of colonization. Early missions might be round trip. Go to Mars, establish infrastructure, return home. But as the colony matures, more people might choose to stay permanently, building lives and raising families on Mars. This brings us back to children. The first child born on Mars would be a milestone in human history, but that child would face unique challenges. Growing up in low gravity could affect physical development in ways we can't predict. Their immune system would develop in a radiation-rich environment. Psychologically, Mars would be the only home they've ever known. Earth would be an abstract concept, a place they've seen in videos but never experienced. Would a child born on Mars be able to travel to Earth? If low gravity has permanently altered their skeletal and muscular development, Earth's gravity might be crushingly uncomfortable or even dangerous. They might be Martians in the truest sense, native to Mars, adapted to it, unable to live anywhere else. This is simultaneously fascinating and sobering. It means that Mars colonization isn't just about expanding human presence, it's about creating a new branch of humanity, diverging from our Earth-born ancestors. Education on Mars would be critical. Children would need to learn not just traditional subjects like mathematics, science, and literature, but also survival skills specific to Mars, spacesuit operations, emergency protocols, resource management. They'd grow up understanding that their environment is actively hostile, that vigilance and knowledge are literally matters of life and death. Yet they'd also grow up with a sense of wonder and possibility that Earth-born children might not have. They'd be part of something historic, something bigger than themselves. Let's talk about timescales. When could all of this actually happen? NASA's current plan, the Artemis program, aims to return humans to the Moon by the mid to late 2020s. The Moon serves as a proving ground for technologies and techniques that will be needed on Mars. We'll test life support systems, habitat designs, and in situ resource utilization on the lunar surface before attempting the much more difficult journey to Mars. SpaceX, led by Elon Musk, has set ambitious timelines for Mars missions. Musk has talked about sending uncrewed cargo missions to Mars by the late 2020s, followed by crewed missions in the early 2030s. These timelines are aggressive, and many experts are skeptical they can be met. But SpaceX has a track record of achieving things that seemed impossible: reusable rockets, private crewed missions to the ISS, the development of Starship, the largest and most powerful rocket ever built. China has also announced plans for Mars missions, including sample return and eventual crewed landings. The geopolitical landscape of space is changing. Mars won't be explored by a single nation, but by multiple countries and private entities. This could lead to competition, but also cooperation. The challenges of Mars are so immense that collaboration might be the only viable path forward. Realistically, the first human boots on Mars are probably 10 to 20 years away. A permanent, self-sustaining colony might take 50 to 100 years. These are long timescales, but they're not unreasonable. Human history is filled with multi-generational projects, cathedrals that took centuries to build, explorations that spanned decades. Mars is our generation's cathedral, our great work. Now let's explore something that often gets overlooked: the beauty of Mars. When we talk about survival and engineering challenges, it's easy to forget that Mars is a place of stunning natural wonder. Olympus Mons, the largest volcano in the solar system, rises 21 kilometers above the Martian datum. That's more than twice the height of Mount Everest. Its base is the size of Arizona. Standing at the summit, the horizon would curve away in all directions, and you'd be able to see the curvature of Mars itself. Valles Marineris is a canyon system that stretches over 4,000 kilometers, nearly a quarter of the way around Mars. It's up to 7 kilometers deep and 600 kilometers wide in places. The Grand Canyon on Earth could fit inside one of its side branches. Imagine hiking along the rim, looking down into a chasm so vast that clouds form in its depths, so deep that the far wall fades into atmospheric haze. Mars has ice caps that wax and wane with the seasons. During winter, carbon dioxide freezes out of the atmosphere, and the polar caps grow. In spring, the ice sublimates directly from solid to gas, creating geysers and dark streaks as dust is lifted from beneath the melting ice. There are sand dunes of incredible variety, some shaped by wind into perfect crescent forms, others forming vast seas of rippling patterns. There are impact craters everywhere, each one a window into Martian history. Some craters are pristine, with sharp rims and rays of ejected material. Others are ancient and eroded, barely visible depressions in the landscape. Some craters have central peaks formed when the impact's energy caused rock to rebound upward. Each crater tells a story of cosmic violence, of asteroids and comets that struck Mars millions or billions of years ago. And then there are the sunsets on Mars. Sunsets are blue. This happens because dust particles in the Martian atmosphere scatter light differently than our atmosphere does. Blue light penetrates the dust more effectively, creating a blue glow around the sun as it sets. It's a reminder that you're on an alien world where even the sky behaves differently. The night sky on Mars would be a revelation. With no moon to brighten the sky, well, Mars does have two moons, Phobos and Deimos, but they're tiny, irregularly shaped chunks of rock. The stars would be brilliant. Phobos orbits so close to Mars that it crosses the sky 3 times a day, appearing larger when overhead and smaller near the horizon. It's tidally locked, always showing the same face to Mars. Deimos is smaller and farther out, taking 30 hours to orbit. From Mars, you could watch Earth and the Moon together, appearing as a double star system. Through a telescope, you could see continents on Earth, track storms, watch the lights of cities on the night side. It would be a constant reminder of home, both comforting and melancholy. Let's talk about the journey itself, getting to Mars in the first place. This is no short trip. Depending on the alignment of Earth and Mars, the journey takes between 6 and 9 months using current propulsion technology. That's half a year to nearly a year confined in a spacecraft, living in microgravity, exposed to cosmic radiation, with no possibility of turning back once you've committed to the trajectory. The spacecraft would need to be much larger and more sophisticated than anything we've sent to Mars before. It would require living quarters for the crew, life support systems, radiation shielding, exercise equipment, food storage, water recycling, and all the supplies needed for the journey, plus the initial setup on Mars. It would probably be assembled in orbit around Earth rather than launched in one piece, because it would be too massive to lift directly from Earth's surface. During the journey, astronauts would face multiple hazards. Radiation exposure would be significant, perhaps equivalent to several hundred chest X-rays over the course of the trip. Without Earth's magnetic field to protect them, cosmic rays would pass right through the hull. Some spacecraft designs include water walls, tanks of water surrounding the crew quarters that serve double duty as radiation shielding and emergency water supply. Microgravity would cause muscle atrophy and bone loss, just like on the International Space Station. Astronauts would need to exercise for several hours every day to minimize these effects. Even so, they'd arrive at Mars weakened, needing time to adapt to Martian gravity before they could function at full capacity. Psychologically, the journey would be grueling. You'd be confined with the same small group of people for months. There would be no privacy, no escape, no fresh air or natural light. The Earth would gradually shrink behind you until it was just another point of light. Mars would slowly grow ahead of you, transforming from a reddish star into a disk and finally into a world. Communication delays would increase as you traveled farther from Earth. By the time you're halfway to Mars, there's a delay of several minutes each way, making real-time conversation impossible. You'd rely on recorded messages, emails, and video logs. Mission control would still be there, monitoring systems and providing guidance, but you'd be increasingly on your own. And then there's the landing. Mars's atmosphere is thick enough to require heat shields but too thin for parachutes alone to slow a heavy spacecraft safely to the surface. NASA has developed a technique called supersonic retropropulsion, firing rockets while still traveling at supersonic speeds to slow the descent. The landing of Perseverance in February 2021 using the sky crane maneuver was a masterpiece of engineering. But landing humans with all their equipment and habitat modules would be far more complex. You'd need precision. You'd need to land near resources, water ice ideally, and in a location that's scientifically interesting but relatively safe. Flat terrain, not too many rocks, protected from dust storms if possible. The landing would be the most dangerous few minutes of the entire mission. Systems failures, unexpected terrain, wind gusts, any of these could be catastrophic. But let's say you land successfully. You step out onto the Martian surface, the first human to set foot on another planet since the Apollo astronauts walked on the Moon decades ago. What do you feel? Exhilaration, certainly. Pride, maybe fear, definitely awe. You look around at a landscape no human has ever seen with their own eyes, and you realize this is history. This moment will be remembered as long as human civilization exists. The first tasks would be immediate and practical. Deploy the habitat modules. Set up solar panels or nuclear reactors. Establish communication with Earth. Check all systems. Ensure everyone is healthy and adapting to Martian gravity. The first days would be a whirlwind of activity, adrenaline and excitement masking the fatigue from the journey. Then the real work begins, building the infrastructure for long-term survival, mining ice and processing it into water, testing the soil for agriculture, setting up laboratories to study Martian geology and search for signs of life, exploring the surrounding area. Every day would bring new challenges and new discoveries. One of the fascinating aspects of living on Mars is that you'd be doing science constantly. Every rock you pick up, every sample you analyze, every weather pattern you observe contributes to our understanding of Mars. You'd be geologist, biologist, chemist, and meteorologist all at once. The data you collect would be transmitted back to Earth, where scientists would analyze it and send back questions and hypotheses for you to test. You'd be part of a global scientific collaboration spanning 2 planets, but you'd also be an engineer and a problem solver. Things would break, equipment would fail. You'd need to improvise, adapt, repair systems using whatever materials you have available. Remember the famous scene from Apollo 13, where engineers on Earth had to figure out how to fit a square carbon dioxide scrubber into a round hole using only the materials available on the spacecraft? That kind of creative problem solving would be a regular part of life on Mars. There's something profound about this. On Earth, we're surrounded by infrastructure we take for granted. If your car breaks down, you call a mechanic. If your plumbing fails, you call a plumber. On Mars, you are the mechanic and the plumber. You and your crew are the entire support system. Self-reliance and technical skill aren't just valuable, they're essential for survival. This brings us to the concept of redundancy. On Mars, every critical system needs backup systems, and those backup systems need backups. If your primary water purifier fails and you don't have a replacement, the mission is over. If your life support system has a single point of failure, one malfunction could kill everyone. Engineers designing Mars missions think in terms of triple or even quadruple redundancy for essential systems. This philosophy extends to skills as well. Every crew member needs to be cross-trained. If your only doctor becomes incapacitated, someone else needs to be able to handle medical emergencies. If your primary engineer is injured, others need to be able to maintain critical systems. Everyone needs to know how to repair spacesuits, operate the rover, grow food, and perform emergency procedures. Let's talk about medicine on Mars. Healthcare would be one of the most challenging aspects of the colony. You can't airlift someone to a hospital if they have a medical emergency. There's no ambulance, no ER, no specialist surgeons. The crew would need a medical officer, probably someone with extensive training in emergency medicine, surgery, and dentistry. They'd need a well-stocked medical bay with equipment for everything from routine checkups to emergency surgery. But some things would be impossible to treat on Mars, at least initially. A severe heart attack, a stroke, a complicated pregnancy. These could be death sentences. This is one reason why crew selection is so rigorous. You choose people in peak physical health with no predisposition to major medical conditions. You screen out anyone with genetic markers for diseases that could become life-threatening. Telemedicine would help. Doctors on Earth could guide the crew through procedures via video link, even with the communication delay. Surgical robots might eventually allow Earth-based surgeons to operate remotely. But in emergencies, the crew would be on their own, relying on training, protocols, and whatever medical knowledge they have. There's also the question of mental health care. Isolation, stress, fear, grief. These are inevitable on Mars. The crew would need psychological support, both from each other and from professionals on Earth. Regular check-ins with psychologists, access to therapy, medication for anxiety or depression if needed. Mental health would be monitored as carefully as physical health because a psychological crisis could jeopardize the entire mission. Now let's imagine you've been on Mars for a year. The initial excitement has settled into routine. You've faced challenges, solved problems, celebrated victories. You've watched Earth in the night sky and thought about everyone you left behind. You've grown food with your own hands, breathed air you manufactured, lived in a habitat you helped build. You've explored landscapes that no human has ever seen before. You've collected data that will advance science for decades. And maybe, just maybe, you've found something, a microbial mat in a subsurface ice deposit. Organic molecules in rock layers that suggest ancient biological processes, chemical signatures that can't be easily explained by geology alone. You don't have definitive proof of life yet. That would require more sophisticated analysis than your equipment allows, but you have enough to know that the question is no longer hypothetical. Life on Mars is possible, maybe even probable. This discovery would transform everything. It would mean that life arose independently on at least 2 worlds in our solar system. It would suggest that the universe is teeming with life, that biology is a natural outcome of chemistry given the right conditions. It would be the most important scientific discovery in human history, reshaping our understanding of our place in the cosmos. But even without such a discovery, the presence of humans on Mars would be transformative. It would represent a fundamental shift in human civilization. For all of recorded history, humanity has been a single planet species. Every person who has ever lived, every civilization that has ever risen and fallen, every war, every work of art, every moment of joy and sorrow, all of it has happened on Earth. Mars would change that. We would become a multi-planetary species with human consciousness existing in 2 places at once, separated by millions of kilometers of space. This isn't just a technological achievement. It's a philosophical and existential milestone. It means that no single catastrophe, no asteroid impact, no nuclear war, no pandemic, no environmental collapse could extinguish human civilization entirely. If Earth were to suffer a catastrophic event, humanity would endure on Mars. And if Mars faced disaster, Earth would remain. We would have insurance, a backup, a hedge against extinction. Some people criticize this thinking. They argue that we should fix Earth's problems before we go to Mars, that spending billions on space exploration is irresponsible when we have poverty, disease, and climate change to address. It's a fair critique, and it deserves a thoughtful response. The truth is, we don't have to choose. The resources devoted to space exploration are a tiny fraction of global economic activity. NASA's entire annual budget is less than 0.5% of the United States federal budget. The technologies developed for space have applications on Earth: water purification, renewable energy, medical devices, materials, science. Solving the challenges of living on Mars helps us solve the challenges of living sustainably on Earth. More fundamentally, exploration is part of what makes us human. We've always looked beyond the horizon, wondered what lies over the next hill, crossed oceans and continents in search of new lands. Mars is the next frontier. It calls to the same impulse that drove ancient Polynesians to navigate the Pacific, that sent European explorers across the Atlantic, that pushed humans to the poles and the depths of the ocean. We explore because we're curious, because we seek knowledge, because we want to know what's possible. And there's a practical argument too. Earth won't remain habitable forever. In about 1 billion years, the sun will have grown hot enough that Earth's oceans will evaporate. In 5 billion years, the sun will expand into a red giant and consume the inner planet. These timescales seem impossibly distant, but they're real. If humanity is to have a long-term future, measured not in centuries but in millions or billions of years, we need to become a spacefaring civilization. Mars is the first step. Let's return to the daily experience of living on Mars. One of the things that would strike you immediately is the silence. On Earth, we're surrounded by sound. Wind rustling leaves, birds singing, distant traffic, other people talking. On Mars, outside your habitat, there's almost no sound. The atmosphere is so thin that sound barely propagates. You might hear your own breathing inside your helmet, the crunch of regolith beneath your boots, the mechanical sounds of your spacesuit. But otherwise, silence. Profound, deep, almost unsettling silence. Inside the habitat, it would be different. The hum of machinery, the whoosh of air circulation, voices of your crewmates, music playing from speakers. Sound would become precious, a reminder of life and activity in an otherwise silent world. You might find yourself listening to recordings of earth sounds, rain falling, ocean waves, forests full of birds, just to feel connected to the living world you left behind. Smell would be another strange thing. On Earth, our sense of smell is constantly engaged. Fresh bread, flowers, rain, cut grass. On Mars, inside a sealed habitat with recycled air, everything would smell sterile and mechanical. You'd smell metal, plastic, cleaning chemicals. The greenhouse might offer relief, the earthy smell of plants, the green scent of growing things. It would be a small pleasure, but a significant one. Food would become one of the great joys and challenges of Martian life. As I mentioned earlier, you'd be eating a combination of pre-packaged meals from Earth and fresh produce grown in the greenhouse. But the psychological importance of food can't be overstated. Sharing a meal is one of humanity's oldest social rituals. Cooking together, eating together, celebrating special occasions with special foods. These activities would help maintain morale and social cohesion. Imagine celebrating a birthday on Mars. Your crewmates might surprise you with a cake made from stored ingredients, decorations printed on the 3D printer, a small party with music and laughter. Or celebrating holidays, Christmas, Diwali, Lunar New Year, whatever traditions the crew brings from Earth. These moments of joy and community would be vital for psychological health. There would also be new Martian traditions. The anniversary of your landing, the first successful harvest from the greenhouse, the day someone found something particularly interesting in a rock sample. These would become shared experiences that bind the crew together, creating a sense of community and purpose. Let's talk about exploration beyond the initial landing site. Mars is vast, and there's so much to see and study. You'd want rovers, both robotic and human-driven, to explore the surrounding region. Imagine driving across the Martian landscape, navigating around craters and boulders, watching the horizon rise and fall. You'd be a modern-day Lewis and Clark, mapping unknown territory, discovering features that have never been seen up close. You might explore ancient river channels looking for evidence of where water once flowed. You might climb the flanks of extinct volcanoes, studying the layers of lava that tell the story of Martian geological history. You might descend into canyons, examining the exposed rock layers like pages in a book, each one revealing a different chapter of Mars's past. And you'd be looking for water ice. Water is the most critical resource on Mars. Finding accessible ice deposits would be a game changer for the colony. It would mean a virtually unlimited supply of water for drinking, agriculture, and manufacturing. It would mean oxygen to breathe and hydrogen for fuel. Some of the most promising locations for water ice are in the mid-latitudes, where radar has detected subsurface ice just a few meters below the surface. Drilling for ice would be a major operation. You'd need specialized equipment to dig through regolith and extract the ice without contaminating it. You'd need to process it, purify it, and store it. But once you have that capability, the colony's sustainability increases dramatically. You're no longer entirely dependent on supplies from Earth. You're beginning to live off the land. This concept, living off the land or in situ resource utilization, is central to making Mars colonization viable. Every kilogram of material you don't have to bring from Earth is a kilogram you can use for something else. If you can manufacture your own water, oxygen, building materials, and fuel on Mars, the cost and complexity of resupply missions drops dramatically. One of the most exciting prospects is manufacturing rocket fuel on Mars. The Sabatier reaction, named after the French chemist Paul Sabatier, combines carbon dioxide from the Martian atmosphere with hydrogen to produce methane and water. Methane is an excellent rocket fuel. If you can make fuel on Mars, return trips to Earth become much more feasible. You don't have to carry all your return fuel from Earth. You make it on Mars. SpaceX's Starship is designed with this in mind. It uses methane as fuel specifically because methane can be manufactured on Mars. A Starship could land on Mars with empty fuel tanks, produce fuel using Martian resources, and then launch back to Earth. This makes reusable interplanetary spacecraft practical. Let's talk about what happens when things go wrong, because they inevitably will. Space exploration has a history of near disasters and heroic recoveries. Apollo 13 is the famous example, an oxygen tank explosion on the way to the Moon that could have killed the crew but didn't because of quick thinking, creative problem-solving, and incredible teamwork between the astronauts and mission control. On Mars, you'd face similar crises. A micrometeorite punctures the habitat wall, causing rapid depressurization. A dust storm damages your solar panels, cutting power. A crew member is injured during an EVA. A critical component fails with no replacement. Each of these scenarios requires preparation, training, and the ability to stay calm under pressure. The key is anticipating failure modes and having contingency plans. You practice emergency drills regularly. You maintain detailed repair manuals and spare parts inventories. You cross-train so that multiple people can handle critical tasks. And you cultivate a culture of problem-solving and resilience where challenges are met with determination rather than panic. There's a concept in spaceflight called "failure is not an option," famously attributed to NASA flight director Gene Kranz during Apollo 13. On Mars, this mindset would be essential. When you're millions of kilometers from help, failure truly isn't an option. You find a way, or you don't survive. This creates intense pressure, but it also brings out the best in people: creativity, courage, determination, and teamwork. Let's consider a specific scenario. Imagine there's a major dust storm approaching your base. Martian dust storms can be enormous, sometimes engulfing the entire planet for weeks or months. The storm won't physically damage your structures. Despite what the movie The Martian portrayed, Martian winds aren't strong enough to knock things over due to the thin atmosphere. But dust blocks sunlight, which means your solar panels stop generating power. You'd need to prepare. Check battery reserves, reduce power consumption to essential systems only, secure anything outside that might get buried in dust, hunker down and wait it out. During the storm, the world outside turns orange-red, visibility drops to near zero, and the temperature falls as sunlight is blocked. Inside the habitat, you'd maintain minimal operations, conserving power, perhaps rationing food, if the storm lasts longer than expected. This is where nuclear power becomes attractive. A small nuclear reactor wouldn't be affected by dust storms. It would provide steady, reliable power regardless of weather conditions. NASA has been developing kilopower reactors specifically for this purpose: compact, safe, autonomous systems that could power a Mars base for years without refueling. Communication during emergencies would be critical. You'd need to keep mission control on Earth informed of your status, even with the time delay. They'd be analyzing data, running simulations, consulting with experts, and sending recommendations. But ultimately, the crew on Mars would make the final decisions. They're the ones on the ground, experiencing the situation firsthand. They have the most complete information, even if mission control has more analytical resources. Now let's think about what happens as the colony grows. The first mission might be just 6 to 12 people, but over time, As more missions arrive, the population would increase. 20 people, then 50, then 100. Each new arrival brings more skills, more perspectives, more hands to do the work. The infrastructure expands, more habitats, more greenhouses, more laboratories, more industrial capacity. At some point, the colony reaches a critical threshold where it becomes self-sustaining. It can produce enough food, water, oxygen, and energy to support itself indefinitely. It can manufacture most of the tools and components it needs. It still relies on Earth for complex electronics, specialized equipment, and certain raw materials, but it's no longer one broken component away from disaster. This is when Mars stops being a research outpost and becomes a true colony. People start thinking in terms of permanence rather than tours of duty. They make long-term plans. They invest in infrastructure that won't pay off for decades. They start families. The first Martian-born generation grows up, and suddenly you have people who've never been to Earth, who consider Mars their home. The architecture of the colony would evolve. Early habitats are functional and utilitarian, metal cylinders buried under regolith, purely focused on survival. But as the colony matures, there would be room for aesthetics, for beauty, for spaces designed for comfort and well-being rather than just efficiency. You might have public spaces, a commons area with plants and art, windows looking out over Martian vistas, places for people to gather and socialize. There would be streets, or their equivalent, pressurized tunnels connecting different modules and buildings. Perhaps eventually a central dome, a large pressurized space where people could walk around without spacesuits, breathe freely, feel a sense of openness. Trees might grow there, reaching toward artificial sunlight. Children might play in low-gravity playgrounds, launching themselves through the air in ways that would be impossible on Earth. Education would become crucial as the colony grows. You'd need schools for the children born on Mars. What would the curriculum look like? Standard subjects like math, science, language, and history, certainly. But also Martian-specific knowledge, the history of Mars exploration, areology, Martian geology, life support systems, survival skills. These children would grow up bilingual in a sense, fluent in both Earthling culture, which they'd learn from books and videos, and Martian culture, which they'd live every day. There would be cultural exchange with Earth, but also cultural divergence. Martian colonists would develop their own slang, their own idioms, their own ways of seeing the world. Earth-centric phrases wouldn't make sense on Mars. You wouldn't say down to Earth to mean realistic, or talk about being over the moon with happiness. New expressions would emerge, rooted in Martian experiences. Maybe solid regolith would mean something reliable, or clear sky would mean a stroke of good luck when dust storms are the norm. Sports and recreation would adapt to low gravity. Basketball on Mars would be wild. You could jump 3 times higher than on Earth. Imagine dunking from the free throw line. Running would feel like bounding, each step carrying you much farther. New sports might be invented that take advantage of Martian conditions. Zero-gravity sports in pressurized chambers, competitions unique to the environment. Art would flourish. Painters would capture Martian landscapes in ways that photographs can't quite convey. Musicians would compose pieces inspired by the alien environment. Writers would tell stories of exploration, survival, and discovery. The first truly Martian art movement would emerge, distinct from anything on Earth, because it's created by people living in a fundamentally different environment. And there would be philosophy and spirituality. Living on Mars would raise profound questions. What does it mean to be human when you're no longer on humanity's home planet? How do religious traditions developed entirely on Earth apply to life on another world? Are Martian colonists still Earthlings, or are they something new? These questions wouldn't just be academic, they'd be lived experiences shaping identity and worldview. Some people might find spiritual significance in the Martian landscape itself. The ancient, cratered terrain that has remained virtually unchanged for billions of years, the silence and stillness, the stark beauty. There's something almost sacred about untouched wilderness, and Mars is the ultimate wilderness, an entire planet that has never known life, never been altered by biology, existing in a state of geological purity. Let's think about the long-term future, decades or even centuries ahead. If colonization succeeds, if the population continues to grow, Mars could eventually have cities, real cities with tens of thousands or even millions of inhabitants. Imagine a metropolis built into Valles Marineris, structures climbing the canyon walls, bridges spanning the gaps, the entire canyon turned into a habitable space, or a city inside a lava tube, a naturally sheltered environment where you could build upward in low gravity, creating structures dozens of stories tall. The ceiling of the lava tube, kilometers above, would be covered with lights simulating a sky, perhaps even displaying images of Earth's sky, clouds drifting past, stars at night. Transportation between cities would require infrastructure, pressurized trains running through tunnels, roads for rovers carrying cargo. Eventually, perhaps, a Martian hyperloop, evacuated tubes where vehicles can travel at extraordinary speeds without air resistance. The trip from one side of Mars to the other could take just a few hours. Resource extraction would expand, mining operations pulling valuable minerals from the Martian crust, processing facilities turning raw materials into finished goods, manufacturing hubs producing everything from spacesuits to solar panels to computer chips. Mars wouldn't just consume resources, it would create wealth, exporting goods and knowledge to Earth and other human settlements in space. And there would be other settlements. The asteroid belt holds vast mineral wealth. The moons of Jupiter and Saturn offer exotic environments for research and perhaps colonization. Mars would be the hub, the waypoint between Earth and the outer solar system. Ships departing from Mars wouldn't have to fight Earth's deep gravity well, making launches cheaper and easier. Mars could become the shipping and industrial center of human civilization in space. But all of this depends on that first step, landing humans on Mars and keeping them alive. Every grand vision starts with a single footprint in the red dust. Everything else follows from that moment of arrival, when humans first stand on Martian soil and look up at the stars, knowing they've taken humanity's first real step toward the cosmos. There's another dimension to Mars colonization that we haven't fully explored yet: governance. How would a Martian colony be governed? Who makes the laws? Who enforces them? These aren't abstract questions, they have real implications for how the colony functions and whether it succeeds. Initially, governance would probably be straightforward. The first missions would be organized by space agencies or corporations with clear chains of command. The mission commander would have authority, similar to a ship's captain. Decisions would be made based on mission protocols, safety considerations, and directives from Earth. It would be functional, hierarchical, focused on survival rather than politics. But as the population grows and the colony becomes more permanent, governance becomes more complex. People want a say in decisions that affect their lives. They want representation, fairness, accountability. You can't run a city of 10,000 people the way you run a research outpost of 12. So, what form of government would emerge? Democracy seems natural. It's what most colonists would be familiar with, coming from democratic nations on Earth. But Martian democracy might look different from Earth democracy. With small populations, direct democracy could be viable. Everyone votes on major decisions. Everyone participates directly in governance. Town hall-style meetings where issues are debated and decided collectively. There's also the question of relationship with Earth. Would Mars be a territory of Earth nations like Antarctica under the Antarctic Treaty, or would it be independent? The Outer Space Treaty of 1967 states that no nation can claim sovereignty over celestial bodies, but that was written before permanent colonization was seriously considered. As Mars develops, there would be pressure to revise these treaties. Martian colonists might eventually demand independence. They'd argue that people living on Mars, facing Martian challenges, should make their own decisions without waiting for approval from Earth. The time delay alone makes Earth-based governance impractical. By the time you send a question to Earth and receive an answer, circumstances might have changed. Local autonomy would be more efficient, but independence brings challenges. Mars would need its own legal system, economic policies, and diplomatic relations. It would need to negotiate with Earth as an equal partner rather than a dependent colony. This could create tension, especially if Earth-based governments or corporations feel they have ownership rights based on their initial investment in colonization. History offers parallels. The American colonies declared independence from Britain. Australia and Canada transitioned from British colonies to independent nations. Each case involved negotiation, conflict, and ultimately a redefinition of the relationship. Mars would likely follow a similar path, though hopefully less violent. Currency is another interesting question. What would Martians use for money? Initially, they might use Earth currencies, dollars, euros, yuan, but a Martian economy might eventually develop its own currency, perhaps based on the colony's productive capacity or tied to specific resources like water or energy credits. Trade between Earth and Mars would be limited by physics. The energy cost of shipping goods between planets is enormous. Only very high-value, low-mass items would be worth trading. Advanced technology, rare scientific samples, intellectual property, data. You wouldn't ship raw materials, the economics don't work. But you might ship pharmaceuticals developed on Mars, or computer chips manufactured in clean rooms with Martian resources, or genetic samples of Martian microbes if they're discovered. Legal questions would arise that have no precedent on Earth. If someone commits a crime on Mars, which jurisdiction has authority? If a child is born on Mars to parents from different Earth nations, what's their citizenship? If someone discovers a valuable resource on Mars, who owns it? These questions would need answers, and those answers would shape Martian society. There's also environmental law to consider. Should Mars be preserved in its natural state, or is it fair game for development? The debate between preservation and exploitation would rage just as it does on Earth. Some would argue that Mars is scientifically priceless, a natural laboratory for studying planetary science and shouldn't be contaminated. Others would argue that Mars's value lies in its potential to support human life, and that development is not only acceptable, but necessary. A compromise might emerge: protected zones where Martian terrain is preserved for scientific study, and development zones where colonization proceeds. Certain areas, maybe the polar ice caps or particularly significant geological features, might be declared off-limits. Others would be open for settlement and resource extraction. Environmental concerns would extend to terraforming. This is the idea of deliberately altering Mars's environment to make it more Earth-like, thickening the atmosphere, warming the planet, perhaps eventually creating conditions where humans could walk on the surface without spacesuits. Terraforming Mars would take centuries or millennia and require technologies we haven't invented yet, but it's theoretically possible. The basic idea is to release Mars's frozen carbon dioxide at the poles, creating a thicker atmosphere and trapping heat through the greenhouse effect. This would warm the planet, possibly allowing liquid water on the surface. You could introduce hardy microbes engineered to produce oxygen through photosynthesis. Over immense timescales, the atmosphere could become breathable, but should we? Terraforming would fundamentally alter Mars, destroying its pristine state. If there's any native Martian life, even microbial terraforming could wipe it out. The ethical implications are enormous. Do we have the right to transform an entire planet to suit our needs? On the other hand, terraforming could save countless lives, make Mars a true second home for humanity, and preserve our species against extinction-level events. It's a question of values. Do we prioritize preservation of the natural state, or do we prioritize expansion of life and consciousness? These debates would shape Martian culture and identity. Are Martians stewards of their world, protecting and preserving it? Or are they pioneers and builders, transforming it to suit human needs? Different factions would have different answers, and the outcome would depend on who holds power and what values they prioritize. Let's shift to thinking about Mars's place in the broader solar system. Mars wouldn't exist in isolation. It would be part of a network of human settlements. The Moon would likely have bases serving as a testing ground and as a source of resources. Helium-3 for fusion reactors, rare Earth elements, and a launching point for missions deeper into space. Asteroids would be mined for metals and water. Some asteroids are thought to contain trillions of dollars worth of platinum group metals. Robotic mining operations or even human crewed missions to particularly valuable asteroids could become economically viable. The resources extracted would support construction projects throughout the inner solar system. Mars would be the natural hub for coordinating these activities. It's centrally located, has resources, and has gravity, which makes long-term habitation healthier than zero-gravity environments. Ships could be built on Mars and launched to the asteroid belt or the outer planets, taking advantage of Mars's lower gravity compared to Earth. The moons of Jupiter, Europa, Ganymede, Callisto are fascinating targets for exploration. Europa, in particular, with its subsurface ocean beneath an icy crust, is one of the most promising places to search for life. A mission from Mars to Europa would still take years, but it would be more feasible than launching from Earth. Saturn's moon Titan has a thick atmosphere and liquid hydrocarbon lakes. It's one of the most Earth-like environments in the solar system, despite being far colder and having a completely different chemistry. A base on Titan would be an incredible achievement, and Mars could serve as a stepping stone to getting there. This is the long-term vision: humanity as a truly spacefaring civilization, with settlements throughout the solar system, connected by trade and communication, diverse in culture and governance, but united by common origin. Mars would be one node in this network, arguably the most important node outside Earth, but not the only one. And perhaps eventually we'd look beyond our solar system. Interstellar travel is far beyond our current capabilities, but it's not impossible. Generation ships, slower than light vessels carrying thousands of people on journeys lasting centuries, or suspended animation, allowing crews to sleep through the voyage, or breakthrough propulsion systems we haven't imagined yet. The first interstellar missions might launch from Mars rather than Earth. Mars-based industry could construct the massive ships required. Martian culture, shaped by generations of living on a frontier, might produce the kind of people willing to embark on such journeys, pioneers by nature, comfortable with risk and isolation. This is speculation, of course, centuries beyond anything we can currently plan. But it's worth thinking about because it illustrates what Mars represents. Not just a destination, but a beginning. The first step away from our home planet, the proof that humanity can survive and thrive beyond Earth, the foundation for everything that comes after. And speaking of incredible discoveries beyond Earth, if you're fascinated by space exploration, you don't want to miss my video at the left side of the screen. The secrets hidden on the moon's far side will absolutely blow your mind. See you there.